Okay, speaking. So, you guys have been well. I haven't. Kind of under the weather, but didn't cancel class yesterday, so I can't cancel class today because the other class is going to get way ahead of you guys. This close to cancel my classes yesterday, but then I was like, students need me. Okay, let's continue. We looked at matrix multiplication. And why it's defined the way it is. Here's another way in which it's useful. It's also useful for many things. But it's useful for representing systems of equations. So that's kind of the phase in which we're segueing into right now. So I'm not going to write out a general one. I'm just going to write out maybe a couple examples. Look at, say, ax plus by cx plus dy f. This is a system of equations. Your a, b, c, and d can be numbers, so can your e and f, but your x and y are the variables that you want to solve for. Now, by equality of matrices, this is equivalent to, of course I can throw each side into a matrix, and that's not really going to change anything because of how matrices work. If this is equal to that, it means the corresponding components are equal, and if the 1-1 component is equal to the 1-1 component, and the 2-1 component is equal to the 2-1 component, we get back this system of equations. And matrix multiplication would give us that. I can actually rewrite the left side more specifically as something like this. If we notice from how we define matrix multiplication, these two would be multiplied by a row times the column, and you would get ax plus by. This would be row times a column, you get cx plus dy. You'll obtain this back. So we can write that. One thing I want you to notice here is that the first matrix kind of holds all your coefficients. That's exactly what it holds. The numbers in front of the variables, they're all nicely packed away into this one matrix here. So this one here holds the coefficients. And because math people are so great at naming things, we call this the coefficient matrix. You'll notice that this guy here holds the variables. We want to solve for. So this guy is called the solution matrix. Because ultimately, if you want to solve the equation, you want to solve for this guy, and that's going to be your solution. This guy here just holds a bunch of constants on the other side, and we call that the constant matrix. Right? So by matrix multiplication, I can look at a system of equations, and I can write it down using matrices. cool things can happen as a result of that. But let's actually just talk a little bit more about the language here. So typically, the coefficient matrix, we tend to call it big A, and the solution matrix, we tend to call it X with a vector symbol over it, and the constant matrix, we tend to call it E with a vector over it. And this yields the generic notation AX equals B. Now every time I write something like that down on the board, it is signifying that I'm thinking about an object like this. I'm thinking of an equation that relates a bunch of matrices where A is going to hold all the coefficients, X will hold all the variables, and B will hold all the numbers on the other side of the equal sign. So whenever this shows up, it just represents some arbitrary system of equations or just one being considered. So. Now, when a system of equations is written in this form, we call it a matrix equation. It has matrices. Right? So this, as generically represented by that, is called a matrix equation. Whenever you see them, they're very typically representing some system of equations. Same kind of guys you've seen in high school, and you probably know how to solve them. Now, there's another representation. Is the following. So let's say I have A, B, C, D, the X, Y, and the E, F. Sometimes it's kind of superfluous to like have these guys around. In general, we'd know the variables that we care about, or at least we'll know that the first column is the coefficient of the x's, the second column is the coefficient of the y's, and these are the numbers on the other side. So a lot of times we would actually write this system down as just one big matrix, where the only relevant information for us is going to be one, the coefficient matrix. What are the guys that are in front of the x's and the y's? We would write a bar here, which is traditional, that represents the equal sign, and we write what should these equations be equal to. And you can just write one big matrix to represent that system, so this is considered equivalent to that. And whenever we do this, we say, we've augmented the system. Because this guy right here, he is called an augmented matrix. So that's just some of the language that we'll be using. So if I ever give you a system of equations and I say augment the system, I mean I want you to write down one giant matrix that represents the system of equations. And that's saying augmented the system. And that also has a generic representation a big matrix, write a big A here, write a bar, write a B here. And so this, whenever it shows up, represents an augmented system. Now, nothing is special about this particular size. You can actually do this for any size. So let's just make sure we get the idea here. Example, let's say I have 2x minus 3y plus 12z equals 4. Add x minus 2z equals 3. Write the matrix equation. And the augmented system. Let's say I gave you that. These are two equations. Notice that we have three unknowns here. Just kind of write down what you think are the answers here, and we'll move on. So what does the matrix equation look like here? So it's going to be this equals that. What's the first guy?
2, negative 3, 12, 1, 0, negative 2, 4,
Okay, so I can see this, I can just write that down. And to augment the system, what would it look like? Just one big matrix. What's the first row?
2,
And then just copy down the second one. You put a bar here, which is really for people to know what you're talking about. Computer wouldn't really put a bar there, but it's supposed to symbolize the equal sign. So it's like you throw away all the middle stuff because it's kind of pointless to write it if you already know what the variables are, and you might not even care what people call them, so it doesn't matter. So this is augmented. Now, I don't know if you've heard this name before when you were doing systems of equations back in high school, but this would be called a 2x3 system, right? The one I had before, it's called a 2x2 system. You might have heard those names. Those names come from the matrix interpretation of the system. So that's why we name it that. So if you have two equations, three unknowns, it's called a 2x3 system. I probably won't write that down at this moment, but that's just something for you to know. Now, let's look at solving the system. Now, solving the system simply means you're going to want to find the values of the variables that will make all equations true all at the same time. Sometimes, and we'll deal with applications of this right now, but for now let's just deal with the theoretical aspect of it. linear equations are so applicable, it's crazy that these simple objects are very applicable in this technologically advanced world, but there are many situations in which you'd want to be able to solve a system of linear equations. Let's actually remind ourselves how to do it. I'm going to remind you of one particular method, and for the basis of comparison, we're going to do it by the elimination method, or the addition method that you may remember from high school. So let's look at 2x plus 3y equals minus 1. And so I'm going to actually do it a little bit different from how you did it in high school. So what I'm going to basically do is pretend that I'm kind of like a computer, and so I'm solving this system using random memory. The moment I don't write down some information, I will forget this information. So I'm going to be changing the information, but I always want to keep two equations moving along. Right? Sometimes you wouldn't do that in solving. You'd isolate one equation and work on one at a time. But we're always going to keep these two at a time. But I'm going to keep working on them, and that's going to allow me to end up telling you what x and y are. So the goal is to find what are the values of x and y that will make this equation true and that equation true at the same time. Now here are some things I can do. Let's say for some reason I didn't like the fact of how it was written. I like to have a 1x on top. I could switch the equations just to be a little more aesthetic. Now, not completely necessary, but that's something I could do. Just by writing the equations in a different order, I'm not changing the answer. So that's pretty self-explanatory, I think. So now, because we want to solve for x and y, the goal would of course be to isolate the x and y. You want to be able to say x equals something and y equals something. And one way to obtain this is to do the elimination method. How that method works is you're going to multiply an equation by some convenient number, that when we add it to the other equation, one of our variables will get cancelled out and only one will survive. If you can do this in as few shots as possible, this is preferable. So let's say I actually want to solve for the y first. So let's say that's what I want to do. So I want to eliminate the x, solve for the y first. How could I do that? I want you guys to remember. Yeah.
You had 2y to the right side, and then plug it 3 plus 2y.
Oh, you're doing the substitution
Oh,
method.
sorry.
I want to do the elimination method.
Oh, okay.
So I want to, yeah. Go.
Multiply the top equation by 2, and then you can eliminate the x's.
Okay, so I can multiply this by 2.
-2.
You want to do -2? Either one can
Yeah,
work,
that would probably
but let's do -2. Sure. So what I just did was I took equation 1 and I multiplied by -2. Let's call that equation 3. Now, again, remember I'm pretending I'm a computer, so this is in my RAM memory. I'm definitely going to keep writing it so I don't actually forget the information. So now those are my pair of equations. Now what can I do?
Add.
I can add them. Now if I add them, what's going to happen? I would have 0x, right? Now I know it's 0, but I'm going to write it down. Again, for comparison, I'm writing down a little more than you would normally write down for a special reason. And then I would have here 7y, and then I would have here -7. Right? So this here was equation 2. I'm calling this equation 1, that equation 2. So this here is going to be equation 2 plus 3. And what I'm going to do here is just rewrite equation 1 because there's no reason to have bigger numbers than smaller numbers. So I'm going to put this back. Now, is there a nice way to actually solve for y right off the bat here? Yeah.
Divide by 7.
Divide this equation by 7, right? So let's call this 4. And what I can do is I can take equation 4 and I can divide by 7. By the way, you can think of this as multiplying by 1/7. But either way, I would have 0x plus 1y, I'm going to write down the 1, equals minus 7. Equals minus 1. So now this is what my system looks like. X minus 2y equals 3. Now notice at this point, since I've already solved for one of the variables, it's pretty easy to stop here and just plug it in there and solve for the x's. But I want to continue this process. But you should know that this step right here is actually pretty convenient in terms of finding the solution. I could actually stop the process right now, but I want to do the same kind of idea to solve for the x. So let's say I wanted to eliminate the x now. Well, I want to solve for the x, which means I need to eliminate the y's. What would I do at this point? How could I do that?
Multiply the bottom by -2.
Okay. You want negative 2?
Or positive 2, sorry.
Oh, can be positive or negative. It almost doesn't matter. We can, instead of adding, we can subtract the equation. That's the thing. So let's say I multiplied this equation. Let's call this equation 5. And I multiplied equation 5 by positive 2. And so I have equation 1 here. And now what can I do? Well, now I can add these. X plus 0x, well, that's just x. This plus that, well, that's 0y. This plus that, that's 1. And then I would have 0x plus, let's put this down, 1y equals minus 1. So here, what I just did was, I call this equation 6. I just took equation 1 and added it to equation 6. And here I just wrote back equation 5. Now what you will notice about this situation, this one is super convenient because now by looking at this, what could you tell me with regards to the solution?
X is 1, y is negative.
Right? I can say x is 1, y, because the first row says that I have 1x plus 0y equals 1. That's the same as saying x equals 1. In here I have 0x plus 1y equals minus 1. So that says y equals minus 1. Now you can go to the beginning and you can check that if I were to plug in those values, if I plug in x equals 1, I would get 2, y equals minus 1, minus 3, 2 minus 3 is minus 1. And if I plug in 1 here, this will become a plus 2, that would be 3. So these values here actually solve this equation. These are the values that make both of these equations true at exactly the same time. Right? This is what we call the solution to the system. Now for linear systems, there are 3 kinds of solutions, but we probably won't talk about that for a couple lectures. But that's the idea. When we talk about we want to find a solution to a system, we want to find values of the variables that will make the system true. Now, I'm going to do this again. And again, like I said, I was extremely cumbersome in writing this down, but it's for the sake of this comparison. I want to really draw this comparison. Okay, suppose, are you done copying? Okay, so suppose I started out with this, but instead, I augmented the system first. So I look at this, and instead I write down 2, 3, minus 1, 1, minus 2, 3. That's how I started. Now, let's, for the most part, just repeat the steps that we did before. So, for aesthetic reasons, I am going to swap the first and second rows. Now, it should be understood, here the 2, 3, the minus 1, the 2, 3, the minus 1, here's the 1, minus 2, 3, here's the 1, minus 2, 3. It's kind of understood here that each row in this matrix represents an equation, right? And so it stands to reason whatever I could do with the equations, I can do with the rows. So at one point I swapped the two equations, right? It didn't really do anything. Maybe it was mostly for aesthetic reasons, but it's a legal thing to do. I can swap the two rows. Now, if I have in mind that I want to solve for the variable over here, I would want to eliminate the variable over here. And so how did we do that? So what I did here is I moved row 2 to the top, row 1 to the bottom. Then what I'm going to do, I want to eliminate a guy in the x part and leave a guy in the y. So what we did was we actually multiplied by -2. So we took row 1 times -2. And then what we did was we added them. Now I put the result in the second part. So when I add this and this, I got 0. When I add this and this, I got 7. When I add this and this, I got -7. And so what this is it's row 1 plus row 2. Now, these symbols here I'm writing down to keep track of what I'm doing, just so you know. I'm always going to be calling it row 1 and row 2. I'm not going to renumber things because that'll get too cumbersome. So every time when I write this down, I'm referring to the row 1 and row 2 of the previous matrix, right? So row 1 from this matrix is this, and I'm adding it to row 2 from the previous matrix, which is that. And I get that. Now here, we went back to the smaller numbers because they're less cumbersome to work with. So I pretty much took the previous row 1 and I divided it back by -2 to get it in a nicer form. So now we're in this situation. The next thing we did was to get the coefficient of y to be 1. So what I did was take row 2 and we divided by 7. Now that got this to be a 1. And I also mentioned that this was actually a pretty convenient situation to be in because I could immediately tell you what the y was and we could plug it into the top one and tell you what the x was. This situation is convenient. It's not the most convenient, but it's pretty convenient. We actually give it a name. This is called the Row Echelon Form. I'll define that precisely soon. So when we have a matrix in this form where it's pretty convenient to actually solve the system, we can just actually stop and start back substituting. We call that a row echelon form. But we decided to go further. So what we decided to do is to repeat the game to get a similar situation at the top for the other variable. So pretty much I wanted to get a 0 in this position and a 1 in this position. So knowing that that's my goal, I'm going to think, how can I get that to happen? And what we did was we took row 2 and we multiplied by 2. And we added those. So if I take row 1 plus row 2, I would get 1 plus 0, minus 2 plus 2, 3 plus a minus 2. And I can put this guy back, take the row 2 and divide back by 2. That'll give me 0, 1, minus 1. Now, this was the most convenient situation. This guy was the guy that we marked double star in the previous set of examples. This one also has a name. He's called the reduced row echelon form. Of the augmented matrix. Now what you notice about this form, solutions can be read off with minimal back substitution. So there are a couple of things here that we can address that I'll make more clear next time. Given a system of equations, I can write it as an augmented matrix. So this is just this one giant matrix. The point of the point is that we want to actually solve the system of equations. We want to be able to talk about the values of the variables. Now, one way to do that is to start with this matrix and manipulate it in some way. How? Well, I would manipulate it exactly the way I would manipulate it if these guys were actual equations, because they are representing equations. Ultimately, I can bring it to a point where the form of this matrix is now such that I can literally read the rows and tell you what the answers are. This is a convenient thing to do. So convenient that we give it a name. There is a sub-maximal convenient form called the Row Echelon Form. And there's another thing that pops up here. There's this kind of entity, 1001. Anyone remember what that guy is?
T, like transverse.
No? A matrix with ones on the diagonal and zeros everywhere else? That's called an identity matrix. So, because the point was, to actually solve this system, what we can do is we can augment it as a huge matrix. We can do things that we can do with equations. The point is, we want to get it to a point where the left side, what's to the left side of the bar, looks like an identity matrix, or at least as close to it as possible. It's not always possible to actually get something that looks that nice, by the way. Once we get the matrix to this form, we'll be able to talk about the solutions. Now, one thing you can note at this point is when you plug a system of equations into your calculator, like your TI-89, this is actually what your calculator does. Right? Your calculator doesn't solve systems like you do in high school. Your calculator solves systems using matrices. Okay? Because it's actually, for a 2x2, you won't really see how this is better. But when you start getting large, and I mean really large, like hundreds and thousands and millions of variables, just moving around these numbers in this way is going to be a lot more efficient. And so this is how computers actually think of systems of equations. And we will be thinking of systems of equations in this way pretty soon. But I just wanted to first go through it without matrices, and just hopefully you can appreciate we're doing exactly the same thing. We're just writing it down in a different way. Right? We're still moving these rows, but it's like our rows now are our equations. And there are some convenient forms that we like because they help us to solve the equation easier. So we'll be doing a lot of this. This process is useful for solving equations. It's also useful for many other things. We'll be doing it a lot. Any questions so far? Now, let's actually put a name to some of these things. What can I do at this point? About 10 minutes left. There are a bunch of definitions I want to give you, but maybe I'll actually, since I already wrote it down on the board, let's talk about these two situations here. What does it actually mean to be in a convenient form, like a row echelon or a reduced row echelon? So let's define the forms. Okay, so one is called the Row Echelon Form. I don't remember where the etymology what the etymology of this word is. Probably German or Latin for something. You know, how math people are. Row Echelon Form. Whenever I'm lazy, I will abbreviate this REF. So you see me write REF, I'm referring to this thing. A matrix is in row echelon form if a few criteria hold. One, any row of zeros, if there are any, there might not be any. or at the bottom of the matrix. 2. The first non-zero number in every row is a 1. Specifically the number 1. There might not be non-zero numbers, so let's say if any. This is we call this guy a pivot or a lead-in one. That's the first thing. The third thing, each pivot is to the right of any pivots above it. 4. Pivots except the bottom. Now if you look at the form that I marked with an asterisk, you realize that that form fulfilled all these criteria. There were no 0 rows, so that didn't really apply. But the first non-zero number in every row was a 1, you realize. You'd also realize that the 1 in the second row was to the right of the 1 that was in the first row. You'd also notice that, except for the 1 at the bottom, the 1 in the top had a 0 right below it. And they only had 0 below it. Now, the reduced Row Echelon form takes us a little bit further. When I'm lazy, I'll call this RREF. One. It's already in row echelon form with one additional criteria. So all of these will be fulfilled except one thing more. Which is that pivots except the top one. We'll also have zeros above them. I.e., pivots are the only non-zero numbers in their column. Now again, you can look at the last thing that I made asterisk with a double star, and you realize that that matrix fulfilled that additional criteria. It maintained all the criteria of the first matrix, but it had one additional thing. There was a point where there was a -2, I believe, that was above the 1 in the second row, and we eliminated that and made it 0. So that translated into this form. Let's actually make sure that we know how to read this. This is going to be important later.
What would this like?
So it should be quick, just a quick example. REF, RR, EF, or neither. We're going to write down a bunch of matrices. We're going to identify them, what form they have. So it should just be a quick read from what we're doing here. It's A. Now we're not doing anything to these guys. I just want you to literally identify what form they're in. And I guess why they're in that form. Copy those all those down and we'll just run through them. You can go ahead and start writing them in. I'm just waiting for a few people to finish writing. Okay, let's run through these. What's the first one? This is REF. Right? Any row of zeros are to the bottom, there are none. First non-zero number in any row is a 1. Ones have zeros below them. That fulfills all the criteria. So that's REF. Why is it not RREF? The 2 is the problem, right? If that was a 0, that would make it an RRE. So you should know when you're not in a form and what you kind of have to do to fix it. We're going to be dealing with that next class. What about this one? Huh?
The RREF.
It is REF. Why?
2.
This is again the problem. Now, any row of zeros to the bottom, there are none. First non-zero number in any row is a 1. The ones are to the right of the ones that are above them. Ones have zeros below them, except the bottom one. And the last criteria is that the ones also have to have zeros above them, and this one does not have a zero above it, so it's not R, R, E, F. That too is in the problem. That is the problem again. Right there for this one, C. Yeah?
R, yeah.
This is R, R, E, F. Again, let's go through the criteria. Rows of zeros, they're at the bottom. First non-zero number in any row is a 1. The ones are to the right of the ones that are above them, so the guy in the second row is to the right side of the guy in the first row. The ones have zeros below them, and on top of that, they also have zeros above them when possible. So the ones are the only non-zero numbers in their column. This is reduced row echelon form. This one. Neither. What's the problem? 2 again. Can we fix that? If the 2 were a 1, that would actually make it. If this were a 1, what would happen? Then it's R, R, E, F. This one. Neither. What's the problem? This guy's a problem. He is the first non-zero number in a row. He's not to the right side of the guy that's above him. So that's a problem. That guy needs to be a 0. This one.
R, R, E.
This is R, R, E, F. Zeros at the bottom. First non-zero number in every row is a 1. The ones are to the right of the ones that are above them. They have zeros below them and zeros above them. Neither. Why? There's a row of zeros smack dab in the middle of this matrix. It should be at the bottom. And if that were at the bottom, it will actually be reduced row echelon form. This one. This is REF. Again, row of zeros at the bottom. First non-zero number in every row is a 1. They are to the right of the ones that are above them. They have zeros below, but they do not have zeros above. We need to eliminate these guys to make them reduce. We'll pick up with that next class. Eventually we'll start doing some pretty cool work.